Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Rambus with Steve Wu. We're going to talk today about critical factors in storing data in memory. Steve, when we think about storing data in memory, what comes to mind for most people are things like latency and bandwidth and capacity, but there's a lot more than that, right?
That's right. Yeah, those are important factors. But what we're seeing today with memory becoming so important in so many different kinds of systems, there's actually an additional set of parameters that have been coming to the forefront. And their importance is a little bit different depending on the market that you're talking about.
Let's take a closer look.
Sounds good.
Steve, I think most people are familiar with the three items on the left, the latency, bandwidth, and capacity. What are they? How do they change? What's new there, and how does that feed into everything else that's going on?
Yeah, that's a great question, Ed. So, yeah, like you mentioned, latency, bandwidth, and capacity are, pretty well talked about. Very quickly. Latency is just how long does it take me to get data from my memory device. Bandwidth is how much data can I move per second between the host and the memory device. And then capacity is how many bits can I actually store in my memory device.
Latency under load takes things in a completely different direction, though, right? This is more of a customized design.
Yeah. So some of the newer parameters are things like latency under load, fill frequency, power, ECC, and reliability and cost. And you mentioned latency under load, so let me take a moment to explain that. And it turns out that latency, or how long it takes me to get my data from my memory device, it's not just one simple, straightforward parameter. It really depends on kind of the load that my system sees. So a simple analogy would be if you live in a big city or something like that, and you want to go from point A to point B on the freeway, it takes you a different amount of time depending on how much traffic there is on that freeway. Well, memory systems are no different. In fact, if you take a look here at a typical what we call latency under load curve, you can find that under certain situations, as we demand more bandwidth from our memory system, that the latency will change and it'll start to rise. And eventually, when you get towards kind of the peak bandwidth that the system can provide, you'll start to see the latency go up and up and up. And in fact, if you look at different kinds of memories, you might have different curves. For example, the red curve here and the blue curve. In general, we like to see things like the blue curve. We like it to be as flat as possible to maintain the lowest latency that we can across as much of the load as possible. And that helps application designers because it means that no matter how much bandwidth is being pulled from the memory system, they can count on a relatively constant latency. What we don't like to see is something that looks more like the red curve, where the latency can dramatically vary depending on the amount of load in the system.
And the heavy workloads that this will affect are things like AI, right? I mean, you think about a large language model, it's going to be very different behavior than, say, we're just looking for something on search.
Yeah, typically what we see in these large language models and in AI in general are there are large phases in these applications that are heavily bandwidth dependent. They're limited by how quickly you can move data in and out of the memory system. So you're going to tend to operate, more to the far right on this kind of a curve. There are other kinds of applications, though. There can be things that don't use memory very much, for example, or there can be things like pointer chases, things like that, where you're really loading the memory system much less. So it really does depend on the kind of application you're running. And it also depends on things like if I'm in a multi-core kind of processor where I could have many, many different types of programs running all at the same time, that in aggregate, they're all kind of trying to access the same memory system. So in aggregate, we'll tend to push our use case over to the right as well.
And you think about a hyperscale data center, for example, they may be processing a fair amount of data, then it may move over to the next server and next set of memory too, right?
Yeah. In some cases where we have phased computations or things where we have pipelines where we're moving our data across a number of different processing engines, whether they're CPUs or GPUs or something else, you can actually have different characteristics on each processor depending on what stage of the pipeline you're in.
What about fill frequency? What happens there?
Yeah. So fill frequency is another really interesting characteristic. What that is it's the ratio of the bandwidth of the device to the capacity of the device. And the way to kind of think of it is it's an expression of kind of saying, how long does it take me to either write the entire contents of my memory or to read the entire contents of my memory? The idea here is that in certain types of applications, even in places like AI and graphics, what really matters is, in the case of graphics, for example, when I'm rendering a scene, I'll put my polygons that I'm going to be rendering all into my GDDR memory, for example, and I'll be putting textures and things like that in there. In order to actually render the scene, I've got to get all those triangles out and into the GPU to be rendered, and then to actually be displayed in the frame buffer. And so what matters there, how quickly can I get those polygons in due to the movement in my 3D game, for example, and how quickly can I get them out so I can render them and put them on the screen. So that's an example of fill frequency, and there's other applications where full frequency matters as well, like AI, where in the case of high performance inference, you may have one inference job where you're putting all the information into your DRAM, then you're taking all that information out for the inference calculations to happen, and then you bring in the next inference job. So that ability to kind of cycle the data in and out of the DRAM is what's really important there.
And when you think about power, that's not just is this 1.4 volts or 1 volt. It's a lot more nuanced than that, right?
Yeah, absolutely. So when you think about the power of the device, you care about a couple of things. One is, what is the power to actually, kind of store the data in the device? And then what is the power to move that data back and forth? And it depends a lot on the bandwidth of the device. It depends a lot on, the system construction. So in general, when we talk about data movement, the power is really determined a lot by the distance that we're moving the data. In the case of main memory systems, where we have DIMMs, for example, they can be multiple inches away from the processor. But if you think about having something like a graphics processor or a phone, for example, those distances are much, much shorter. They're less than an inch in some cases. And so that difference in distance, take you a different amount of power, and it may require different kinds of circuits and ways to mitigate signal integrity challenges through things like equalization and things like that, which can take you power.
You think about reliability, which is your next item here. When we thought about DIMMs in the past, it was pretty much you never had to worry about them. You figured they were going to work forever. You never had to think about it. If you wanted to upgrade, you stick more memory in a slot. That's no longer the case, right?
That's right. Yeah. So many, many years ago, so the earliest days of computing, the data rates were low enough, and the channels that we were moving our data on were reliable enough that we really didn't have to worry much about bits being incorrectly transmitted. But as the data rates got faster, people came up with some clever techniques for doing things like error correction and even chip kill, where the DIMM modules started to have not only the DRAMs that were required to hold the data for the program, but there would be one or two extra DRAMs that you could put things like parity information and kind of checksum information that would help us determine that whole block of data if it really did get transmitted correctly. As the systems became more popular, and as we cared more about reliability, some of these extra devices could be used for additional reliability, things like the system could continue to run if one of the DRAMs completely failed. And so that has been kind of a mainstay for the industry, and now reliability has become so important, and that the DRAMs themselves have on-die error correction capability, in part because we're going at such fast speeds, and because we're putting so many bits onto our DRAMs that the individual bit cells are so small that they become prone to errors at times. So what we're seeing in the case of ECC and reliability is it's becoming much more important, and we're taking kind of a layered approach, where in some cases there are multiple layers of ECC and reliability that are built into our systems.
Do you also have more metrics and sensors in there that say this is not working the way it's supposed to?
Yeah, in fact, over time, what we've seen is, the DRAMs now have thermal sensors, for example, on them, so they can determine if the device is heating up beyond a kind of a threshold level or a safe level. There is, for example, the on-die error correction that I mentioned, where the DRAMs basically have the ability, if one bit flips and is incorrect, the DRAM can actually correct that bit before sending the data back to the host. There are counters there that will let the host know that, hey, you're generating a lot of errors. So if you read those registers, you can determine that, oh, maybe something's going wrong with this device. Maybe it's starting to degrade its performance. So you can kind of preemptively do something about it. So those sensors and monitors and counters and things like that, there's a growing number of those to deal with the growing number of effects related to performance and reliability.
In the past, when you were dealing with DRAM, it was sort of assumed that you wouldn't use the DRAM all the time, that you would turn some of it off. Does that affect reliability as well?
Yeah, it does actually. So usually when you're using the device and running it, kind of near its peak performance, that's usually the most stressful time on a DRAM. But what we also see is that, these days, to save power, we get kind of aggressive in certain places of kind of turning on and turning off circuits. And what you can start to see at times is the amount of power that's being dissipated can kind of go up and down relatively quickly. And that kind of thermal cycling can also have reliability impacts. So I would say, as the use cases have evolved and as the programs that we run are more stressful and they run for longer periods of time, you do have to worry about things like thermal cycling as well.
And in the past, when you looked at the cost, typically it was a function of have we got too much inventory out there? Is there not enough inventory, or is there going to be a shortage? Is the cost going to go up? It's gotten a lot more complicated on that side too, right?
Yeah, absolutely. So really, as the industry has continued to shrink the devices to more advanced process nodes, the cost of developing a new technology and the cost of the new process node is going up. And so that has to get factored into how you think about amortizing that cost over the volume of a particular kind of memory. There are other things that we care about too. So, in general, when we have a DRAM technology and we go to the next generation, we put more bits onto a DRAM die. And what that does is it helps us reduce the cost per bit, but we're trying to maintain a relatively similar cost overall for the device. So in general, for example, if you put twice as many bits onto a DRAM device in the next generation, you really want to try and become twice as cost effective, and meaning you really want to try and keep the cost of the device in roughly the same range. There are business dynamics and things like that related to supply and demand, which will move the price in different directions. But in general, when we're manufacturing something, kind of that's one of the bases of Moore's law is we're able to pack more things onto a chip, and and we're able to kind of reduce the cost per bit, for example, in the DRAM industry when we do that.
Steve, all these factors that you were talking about really come together when you get to HBM, right?
That's right. I mean, there's been nothing that's really driven the development of kind of new approaches in memory like the AI boom here. And certainly, when you take a look at HBM, many of the things that we just talked about all come together into this one very advanced device.
So latency, bandwidth, latency under load, costs, they're all part of this, right?
That's right. So let's talk about latency and bandwidth and capacity first. Those are the ones that are probably most important. So, the latency of the device, is good, because by virtue of the fact that these devices, these HBM stacks are put right next to the GPU. So that minimizes the latency. We're very close to the device. So that helps us to move our data quickly back and forth. Bandwidth is extremely important in HBM. So what we have is a GPU here, and we take an HBM device, which is actually composed of a stack of DRAM die, and they hold the bits themselves. In this particular case, we're showing 8 DRAM die stacked together, and that they're hooked to something called a base layer. And that provides the electrical connectivity that allows us to signal very quickly back to the GPU through, in this case, a silicon interposer. We have a lot of wires in HBM. And so what we do is we use a silicon interposer because it allows us to etch our wires very finely and very close to each other. That supports a large number of wires. So if you want to have a lot of bandwidth, having a lot of wires and being able to move that data quickly over those wires is what's important.
You also have a lot of data traffic too, right?
Yeah, that's right. So the actual traffic, through here is very, very high. And when we talked about latency under load, it's very important in this type of device because the load is assumed to always be very, very high. And so in order to support that extremely high bandwidth at a very good latency under load, we have a lot of supporting infrastructure in the device. We have a lot of banks on every channel. We have a lot of individual channels that are designed to support the low latency under high load.
Most of this is going in for high performance computing, AI, right?
That's right, yeah. So when we talk about a structure like this, it is inherently more expensive than your traditional DRAM. Traditional DRAM is just soldered right onto a PCB, and then that PCB also connects to a processor like a CPU or a GPU. What's different here is that our assembly that I mentioned, we use a silicon interposer because we need a lot of wires closely spaced together. Well, that silicon interposer is then mounted on a substrate that's made out of a more traditional material, kind of like the PCBs. And then that whole assembly is mounted right onto our PCB, our motherboard. And so you can imagine with all these different layers, the stacking of the different layers within the HBM device, and then the connection of the whole module together with the GPU, that's just more expensive. But it's a market that will pay for this kind of performance, it will pay for this kind of capacity, and it will pay for this kind of bandwidth.
Well, the cost there is no longer just a single element of we're buying memory. It's now part of a whole system that you're building, right?
That's correct. Yeah. So what you often see is that only the markets that generate the highest amount of revenue can actually use a system like this. It's more difficult to design with from an engineering standpoint, and you typically see people like people in the AI field are using this, where the margins tend to be very high. Or if you tend to be somebody like a cloud service provider making your own kind of processor, you can amortize the cost of the hardware over a much larger service that you generate money on.
How about power? How does that fit in here? Because this takes a fair amount more power to drive these signals, right?
That's right. And so, a lot of power is being spent in the DRAM layers, moving the data in and out. And you can see that if you're on these interior layers, you have to actually do some work to get that heat out through the top of the device and then get it cooled. Each of these layers, these silicon layers, they act a bit like a blanket. They're kind of trapping heat in there. And so one of the challenges, of course, is trying to cool this. In the past, what people have been doing is they put a heat sink over the top of both the GPU and the HBM stack. So they're basically the same height, and they would flow air through that heat sink to try and cool it, very much like a radiator in your car. But what we're seeing now is that the amount of power that's being dissipated in both the GPU and the memory is such that air alone is no longer enough. And so what people are doing now is they're taking these heat sinks on top and they're actually directly contacting a liquid with that heat sink. And so the heat which transfers into the heat sink is quickly wicked away by that liquid as it flows through tubing across the top of that heat sink. So that's kind of the next, really evolution in terms of what we're seeing going forward for AI and HBM systems.
And this gets even more complicated because what's happening on the HBM base die is that that's getting used more than it has been in the past too, right?
That's correct. Yeah. So, as much as the DRAM layers are important in providing data to the GPU, all of that funnels through the base die. And if we're doubling or quadrupling the bandwidth of the HBM stack, then we're having to double or quadruple the bandwidth that is going through the base die. The circuits there have to be designed to support that, and we have to have enough connections to support that as well.
How about reliability? How reliable are these devices compared to the old DRAM?
Yeah, I think one of the key things that's going on these days is because we're putting more bit cells on every layer of the DRAM device, those bit cells are smaller and they're holding really fewer electrons. So just by the consequence of having fewer electrons per bit cell, it means that the reliability is tougher. We have newer effects as well, things like row hammer and things where when you operate the device, they can disturb neighboring bit cells, even though you're not even accessing those bit cells. So reliability is becoming much more important. What we're seeing is we're seeing the actual DRAM die have the ability to do on-die error correction, in fact, to be able to fix certain bits. And then we also have extra bits that are transmitted back to the host. And so the host can actually do its own kind of system level ECC where it institutes its own kind of error correcting codes and kind of checks them to make sure that the data is reliable.
And that doesn't even get into the whole idea that you're building a skyscraper here, and now you have mechanical effects too, right?
That's right. You have mechanical effects, you have thermal effects, and you have other effects where the heat and the what's going on in the GPU, because it's in close proximity to this HBM stack, some of that heat can begin to transfer over. So even if the HBM stack has a moderate level of use, the neighboring heat and things can start to affect what's going on in that stack as well.
So your load is really part of a whole system design.
That's right. And so it's never been more important to consider not only what's going on in the device, but entirely in this complete system design. You have to think a lot about the design and construction of the interposer and the substrate, what's going on around you, like in the GPU, and whatever other neighboring devices happen to be around as well.
Steve Wu, as always, thanks for a great explanation.
Thanks very much, Ed.